Coming to some operational problems. So typically you'll have data that is always deviating. So you'll have some deviation in that data, which is saying that it's still okay, but after a certain range, it is not okay, right? So it's something is off. When you have two variables, so this here shows you a simple Pareto, like within a certain range, they're both okay, but after that, it symbolizes an anomaly. So when you have two variables, it's hard as it is to understand what is causing it. But if you have more, which is actually the case in these systems, it is really difficult to understand the causality of certain variables and how they impact the diagnostic that you get. So for this case, we, for example, use the model to first calibrate the model to what we get from the sensors to make sure that the model is valid. We then simulate a drift in that data. So when you have a drift, and we model that drift in the model itself, and that's something we validate. Can we perform that drift with the model? And the third level, once we have the full validation, we can start to predict anomalies. So basically, it's a reference point which says that the model says that the system actually should be doing something, but the real diagnostic says it doesn't, and that sort of signals a trouble in this operation, and tells you basically something is wrong. So just to give an example here, it's a test rig that we have for the compressors, and you can look at certain causalities and how they impact the behavior of that compressor, and can that behavior deviation be signaled and routed back to an anomaly. So we can share more details into it later on, but in this, I just wanted to give you an overview of things that are possible. So going into more on the system side, so let's look at pipelines and systems. For example, here we have a lot of requirements for distributed energy resources to actually integrate them and to have the right controllers that we have also off the ship. And what we do here is basically use models that are coming using the basic physics, capturing, let's say, the wind conditions, how they impact the power generation, how much of that goes into a battery, can you power an electrolyzer at the same time, these different variations of the ways these can operate, and testing all those controls to how you can operate them in a purely virtual environment. That's something that is made possible with both a combination of these models and the ease of integration into the hardware world. So just two use cases here. So one is with the battery energy storage and hydrogen. The other one is hydrogen refueling. Just to say, all these new projects that need to get to market very fast can be accelerated at a much faster pace with this kind of a technology. Coming to a bit closer to what we have today, what I wanted to show you here was also the impact of a detailed hydraulic model on operations. So just consider here, we have a manifold and we have certain pipes going from that manifold carrying some fluid. And as a demonstration, I've just got a pressure source here, for example. We've vary that from 1 to 2 bar, and the other two pressure sources stay at 1 bar, right? So intuitively, you would expect the flow to go from high pressure to low pressure, but that is not always true, because at certain points, because of this D-junction, could be flow reversal, which means because of a high velocity here, you might have a static pressure drop, which means you start to pull flow in from something that is not intuitive. And very often that leads to a lot of problems in the plants. Basically, you've got, for example, here, some reactor units giving you high conversion, the other ones giving you low conversion. And the simple reason is that the flow that is actually being delivered it's not uniform. It's simply because of the geometries and these D.
Thank you for watching. To learn more about this topic, check out the links in the description. And if you enjoyed what you saw, like the video and subscribe to the channel.